Okay, it looks like that we are recording. Okay, good. So today we are going to see some, I'm going to give a lecture about the OSI model and the TCP/IP protocol suite. So we'll see a lot of definition today. It's not going to be fun because it's a lot of definition, but we need to do this definition to talk. When we talk with experts in the networking field, they will talk with using those definitions. So okay, so when we talk about communication, we have some entity, like for example, this, when you send a packet, there is an entity that we call the source or the sender. That will be the device in the network that create the packet and want to send it. There will be a destination or a receiver. It can be one or it can be several. And we are going to use a communication channel. So it will depend on the technology that we use. It can be, for example, a UTP cable, which is based on copper. It can be fiber optic. It can be the vacuum, if we use, for example, Wi-Fi. It can be, the communication channel can be the water, if we are talking about underwater communication. The medium that we will use will depend about where we want to do the communication to take place. And the word medium is the singular of media. So this is Latin word, and we use medium for singular and media in English. So we are going to see some of the definitions that are here. I'm going to go over the first one. For example, when you have a communication, you have to identify who is the sender and who is the receiver. For example, in the TCP/IP protocol suite, we will use IP addresses to identify them. We need a common language. If we don't speak a common language, we cannot understand each other. So let's say that you have two people that want to speak. One speaks French and the other speaks Spanish, for example. They will not be able to understand each other. Now, let's say that two people want to speak. The first one speaks English and French. The second one speaks English and Spanish. They will be able to communicate. What they have to agree is to use English because this is the common language that they have, and they just have one common language. But if you don't have a common language, a common grammar, there is no way to communicate. We are going to talk about speed and delivery timing. So to make analogy with the USPS postal service, when you send a letter or when you send a package, you can ask for a one-day delivery. You can ask for 2 days delivery, or maybe you want to spend a little less money. What you are sending is not that important. So there, USPS has service where they will not tell you in how many days it will arrive, and it will be very cheap. So of course, the timing is important, no? And you can have also in the protocol, in the networking protocol, you can have confirmation or acknowledgement. So you are familiar with that because in the case of the USPS postal service, you can pay a little more and they can give you proof of delivery. So what they do, they ask the person to sign and they scan the signature and you go to the tracking number, you go to the tracking online and you see the proof of the signature, no? That the person have received the packet that you sent or the letter that you sent, no? So other term that we will see is, for example, message encoding. So I have slides for all these terms because they are very important. So I will go over the slides to specify what is message encoding. For example, message formatting and encapsulation is something that we need to know also. Message timing, message size, on message delivery option. What is a unicast, what is a multicast, on a broadcast. We already have talked about that. So let's talk first about message encoding. So the encoding is to transform a series of bits, which is 1 and 0, into a signal that can travel the medium. So the signal will depend on the medium. For example, if you have a connection between two network devices and you use a copper cable, the signal can be, for example, electrical pulse. Or, for example, it can be a carrier that you are going to modulate in amplitude or in frequency or in phase. So that will be if you have, for example, copper technology. Now, if the medium is fiber optic, what you are sending is pulse of light. So of course, as I was saying, the way that you are going to encode, which is transform the series of bits into a signal that can travel the medium, will depend on the medium. So it's fiber optic, it will be light. If, for example, you want to do underwater communication, we have two technologies for underwater communication. We can use light, but light have a very small range. So if the two devices that want to communicate are close to each other in the ocean, you can use light. Otherwise, we use sound. So we will use acoustic wave. And you know that we know that, for example, whale use acoustic wave to communicate to each other. So dolphins, whale, orca do communicate over long distances through acoustic wave, no? So if you are going to use, for example, the air as the communication media, you will send a radio wave. For example, when you use Wi-Fi, the communication media is the air, the vacuum. And in this case, you use a radio wave. So this is called encoding. Decoding is the inverse operation. So the sender will encode and the receiver will decode. So decode is you receive a signal in the transmission medium and you convert this signal back to a series of 0 and 1. So of course, what you receive will depend on the transmission media, no? As we already mentioned. Okay, so message formatting and encapsulation. So I'm going to talk first the analogy with the USPS postal service. We do have some convention when we send a letter. So let's say that I want to write some news to somebody that is in another place and I'm going to send a letter. So I first take a piece of paper, I write what I need to write, I fold a piece of paper, I insert the piece of paper in an envelope. So inserting the piece of paper in an envelope is called encapsulating. And on the envelope, the convention that we use is that we will put the stamps here on the upper right corner, the destination address here. So who is sending can put the address here in the upper left corner or in the back. I usually put the sender address in the back because it's looked to me less confused. But we do have convention and you have to follow those convention. So encapsulating is a way of adding information for a peer. In this case, the US Postal Service. So the US Postal Service, for them, what you are writing is not important. And by the way, you want this to keep private. You don't want people to know what you are writing. The envelopes is just an additional information, and the envelope is for USPS. Because USPS will find on the envelope the information, will find the name of the destination and the address. And based on this information, they will route your package or they will route your letter to the destination. So this is just adding information for a third party encapsulation. And we will see that in networking, we do also encapsulation, which is adding additional information for a third party. Okay, the format. The format is very important. If, for example, we want to design a communication system, we have to agree, all the pair have to agree how we will format the message, how we will present the message. So if we have a common format, we will be able to talk to each other. Otherwise, it's going to be very difficult, no? Message timing. In message timing, we have these three important items. For example, access method. So the medium, most of the medium that we use are shared by several networking devices. And only one device can communicate at a time. If two devices try to communicate at the same time, it will create what we call a collision. A collision is when we cannot understand what the different devices are transmitting at the same time. So if you take our communication system, the people, normally when several people meet together and they talk, you should just have one person speaking at one time. And this person sometimes makes some pauses, allowing another person to continue the conversation. But we should not talk together at the same time, because it will create what I call a collision. And if several people are talking at the same time, it's, even if we are much more intelligent than the computer, that are not intelligent at all, to tell you the truth, we have difficulty when in a room, several people are talking at the same time. So we try to talk in alternance. So if I talk, you listen to me. And when you want to talk, the rest of the people that are around will listen to the person that is talking. So the access of the medium is the rule that we will follow to start talking or to start transmitting. Flow control. Flow control is also related to timing. So flow control is a way that a network device can tell another network device, please don't send me more data. You already sent me enough data. I didn't have time to process all the data that you sent me. I need some time. I will let you know when I'm ready to receive more data. So this is a way to control the flow of the data. We can imagine that we have, for example, a very powerful computer on another computer that is very slow. And the powerful computer is sending a lot of data to the computer that is slow. So with the flow control, the computer that is slow can halt the powerful computer and tell the powerful computer, hey, don't send me much more data for now. I will let you know when you can proceed. Response timeout. It's something that is also important in the timing. So some networking protocol, when they send data, they need to receive an acknowledgement to be sure that the data was received. So how they work? They send the data and they start a timer. And if the timer time out before they received an acknowledgement, they will resend the data. So until they finally received an acknowledgement saying that the destination did receive the packet. So this is a way to be sure that the packet that I sent have been received. Message size. Why is message size very important? So let's say that I have to send a long message. What we will do normally in a networking protocol, we will cut the long message in small chunks, and we will send small chunk. and the destination will receive all the chunk and will recreate the long message. So why it's a good idea to cut a long message in small chunk? Do you have any idea? Do you have you see a reason why it's better to cut it in small chunk and not transmit a long message without interruption? Yes, but there are reasons that are more important. Exactly. If I have to transmit a long message, let's say that the transmission will last 20 seconds. Since the medium is shared, if I start to transmit during 20 seconds, no other computer will be able to use the medium. So they will suffer what is called starvation. And of course, we don't want that. We want that everybody have the impression that the medium is available for them. So we better don't transmit long message to avoid starvation. It's like, for example, you meet with a friend and this person blah, 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 talk a lot and never let you talk. And so every time that you start to talk, you want to start to talk, this person continue talking and don't let you talk. So that you stay there waiting, and you feel frustrated at one point because this person don't allow you to talk. The same thing will happen if we will allow long message. There is a second very important reason. Is let's say that I allow long message and I'm transmitting a long message and there is some noise in the transmission. So the long message is unfortunately suffer the noise and the receptor did not receive the original message. It received a message that was modified by the noise. So I will have to retransmit the message. If I allow long message, I will have to retransmit a long message. Now, if the system forces me to cut the message in small chunk, if a small chunk suffer noise, I will have just to retransmit a small chunk, but not the whole message. So this is the two main reasons why the communication system cuts the long message in smaller chunk and transmits the small chunk. Okay, message delivery option. We have, for example, what we call unicast. Unicast is one station, the source station, want to send a packet to a specific destination, but there is only one destination. For example, in this case, this PC is sending a packet to this PC. There is only one destination. This is called unicast. Broadcast, you already know what it is. So let's say that this station generates a packet. And this station wants to send the packet to all the other stations. For that, it will use a broadcast. So a broadcast is when you send to all the other stations. You don't send to yourself, but you send to all the other stations. So for example, here the source to all these 4 stations. Multicast, we talk about multicast. So multicast is one to many. So the many will depend of the interest. So for that, we create multicast group. And station can subscribe a multicast group. So let's say that at JSU, we create a radio. And you want to listen to the music of this radio. So you can show interest. You can say, oh, I am interested in listening the music of this radio. So you subscribe the multicast group. So when the radio is transmitting music, you want all the devices that did subscribe to this multicast group to receive a copy. So it's one to multiple. And of course, a station can subscribe and can unsubscribe. If I'm not interested in listening to the music anymore, I just unsubscribe the multicast group. Or I can subscribe several multicast groups if I want. So for that, we have the class D IP addresses. If you remember, those are the IP addresses that start in 224 up to 239. So from 224.0.0.0 to 239, 255, 255, 255, we have multicast addresses. So each of these addresses allow me to create a multicast group. Okay, so when you implement a network protocol, you can implement it totally in software, totally in hardware, or a combination of software and hardware, as we will see. So of course, when you implement something in hardware, it's run very fast. The problem that you cannot update it. Once it's done forever. Okay, because the hardware does not give us flexibility to update. Now, the design of a networking system is very complex. It's like, for example, when you do a long program, a long application, like for example, an operating system. So when you do a long application, you have some technique to break the difficulty when you program. For example, you do modules or you do functions. And inside the function, you encapsulate a specific behavior and you use the function. It makes it much easier to program. So the same thing happened here in the networking world. It's very difficult to design also a networking system. So what they did, they divide the networking system in layers. And in each layer, they encapsulate a specific functionality. So let's say in layer 1, we will have that. In layer 2, we will resolve this kind of problem. In layer 3, we will resolve other kind of problem. This is the idea of dividing a networking system in layers. So you also divide the complexity, okay, because you encapsulate specific function in each layer. Okay, so here they say that a networking protocol define a common format and a set of rules to exchange messages. Yes. So what we call a network protocol is a set of rules that we have to follow in order to achieve a specific communication. So you have a lot of networking protocol that you are using. For example, every time that you use a web browser, there is a protocol that is behind, which is called HTTP, Hypertext Transfer Protocol. And it is based on the client-server model. So your web browser is a client, and you will access a web server. For example, JS, you have a web server. And the URL of this web server is www.jsu.edu. And of course, most of the entity worldwide have a web server, so they can provide information about the services that they offer or what they are doing. No? Other protocol that I'm sure you have heard about is TCP, the Transmission Control Protocol. It's a layer 4 protocol, as we will see. It's not the only protocol that we have in layer 4. It's very famous. Another that you have heard about, I'm sure, is IP, Internet Protocol. It's a layer 3 protocol. So both of them are so famous that the TCP/IP protocol suite have their name. They call it, even if we have a lot of protocol there in the TCP/IP protocol suite, we selected those two protocols to represent what is the TCP/IP protocol suite. Okay, there is something that is called interaction between layers. So look, I say that the network will be divided in layers. This is the TCP/IP protocol suite. It has 4 layers, as we will see. So the lower layer is called the network access layer. Then we have the internet layer, the transport layer, and the application layer. As I was telling you, in each layer, we will have a specific functionality that we are going to encapsulate. So in general, in a stack of layers, layer N provides service to layer N+1. And layer N receives services from layer N-1. So look at, this is layer, let's say, layer 1, layer 2, layer 3, layer 4. If I take layer 3, the transport layer receives services from the layer that is below it, which is in this case, the internet layer. And the transport layer gives services to the layer that is above it, which is in this case, the application layer. So those protocols like HTTP, for example, HTTP is an application layer, it is there. TCP is a transport layer. So HTTP will receive services from TCP because this layer receives services from the lower layer. TCP will receive services from the internet layer, where we have a protocol that is very famous, which is called IP. And here, for example, as a technology, we can use Ethernet. IP will receive services from Ethernet. So you have a certain interaction in between layers. What is important when you design a layer, a system based on layers, is the interaction. Here between layers, you need to define interaction. How the transport layer is going to talk with the application layer, or how the application layer is going to talk with the transport layer. And as long as you define this interaction well, your layering system is going to be successful, which means that you will be able to, for example, change a layer without affecting the other layers. This is what we want to do. We want, for example, to change the internet layer without affecting the transport layer and the network access layer. This is the objective, no? Okay. We use all these protocols together. Some give services to others. And the idea is that by working together, those protocols will give us a comprehensive network communication service. To define those protocols, we have 2 possibilities. An international organization that makes standard can standardize a protocol. So this is the best way normally to do it because it's an international organization. We have several international organizations that define the protocol of TCP/IP, the one that we are using. We will see them. In this case, it is called a de jure standard. When it's done by an international organization, or maybe several international organizations collaborate together to define the standard. Now, there are other standards that were born in companies. Those standards are called de facto standards, like defined by factory. So sometimes a company do a standard, which is a property standard. And the standard, maybe the company decide to release it and let other company to use it. So it's start to spread all over. And at one point, it's become very popular. And many people start to using. to use it. This standard will be called a de facto standard, no? Because it was generated by factories, by industry. Okay, TCP/IP is an open standard. It is freely available. It was designed by the Department of Defense of the United States of America. So it's made of a lot of protocol, and here we have an idea. Here we have the stack of TCP/IP. We have the OSI model that we will see. At one point, there were Apple defined a protocol that is called AppleTalk. So many years ago, when you will buy a Macintosh, a Mac, the protocol that it was using was AppleTalk. And you were only able to communicate with other Mac. It was like that at the beginning, because we didn't have a standard. And there were another company that is called Novell. Novell did a network operating system that was called NetWare. And if you were starting to use Novell NetWare, you were at this time trapped with the solution of Novell, because it was the solution of Novell. So you will have to keep buying hardware from Novell, or hardware supported by the software of Novell, and keep buying new version of the networking system from Novell. So there were no interoperability between a Mac and, for example, a PC where you will install Novell. So of course it's not good for the consumer. So at one point, the world changed, the world of networking changed, and we realized that we were not able to keep going like that, that a company start buying, for example, the solution of Apple and have to keep going and buy Apple all the time to connect the network devices together. That we'll talk AppleTalk. The story of TCP/IP is a very interesting story, and it's the story that have been repeated a lot. That was a project of the Department of Defense, as I was telling you. And when they start this project, they wanted to develop a protocol that could survive a nuclear war. So in a nuclear war, of course, you have the enemy destroy your connection, your link. The enemy sometimes destroy a node that is important for your country, but you want the network to keep going. And as long as there is a path, you want the packet to use the path. So they defined TCP/IP. And it was at the beginning only for the Department of Defense through a project that was called ARPANET. At one point, the Department of Defense decided to release this technology to the people. So big university in the US started to use it. For example, the University of California at Los Angeles, the University of California at Santa Barbara, one University of Utah, and there were also a Stanford Research Institute that started the connection of internet, starting at open level connection and use TCP/IP. And then other important universities joined the project, like, for example, the MIT, Stanford University, Berkeley University. So other universities starting to join the project, and it spread all over the USA and then all over the world. So today, TCP/IP is all over the world, is a standard that we are using. And technology like that started as a military project and ended in our hands are very common. For example, the GPS was a military project exclusively at the beginning. And then at one point, it was released to us. The drone technology was also was military project, uniquely at the beginning. And at one point, I don't know who is the president of the US that released the drone technology to us, but one of the presidents decided, okay, let's give this technology to the people. And I'm sure that they have other technology that they are using that we don't know about it. At one point, they will release it to us, and we will also take advantage of this technology. No? Okay, so look, here we have what we call the OSI model, Open System Interconnection Model. It is made of 7 layers. And here we have the TCP/IP protocol suite. So the TCP/IP protocol suite, as I told you, was started by the Department of Defense. It is much older than the OSI model. So the OSI model, as we will see, was created after as an intent to make something that will be a little more global than TCP/IP, because TCP/IP at the end was born in the USA in the Department of Defense. So they wanted something that was a little more international, and they tried to make an effort developing the Open System Interconnection Model. They make it in 7 layers. Here we only have 4 layers. We will come back to that. This model at the end never got a commercial success. So it is just a model of reference. And we will use it as a model of reference to compare different stack implementation of protocols. So why we use layers? I already told you, for example, to divide the complexity. Another thing that is important, we know in each layer what functionality we are going to encapsulate. So let's say that you have a problem in your network, you identify what is happening. You can know in which layer the problem is happening, because according to the problem that you detect, you know, oh, this functionality is in layer, for example, layer 3. If it's in layer 3, you have to go to the network layer and find the problem. Also, it is very important to define standard, because standard allow different manufacturers to design networking devices that can interoperate together. So you are not married with one manufacturer. You can buy today IBM, connect them with Dell computer, connect them with Apple computer, and they all talk together. Connect them with Cisco router. They all talk together because we have standard. So it's very important to promote or to foster the competition between manufacturers, so we get better product and with a lower price. So why it's important also to do layer, as I was telling you, you may want to change the network layer. And if you want to change the network layer, you want not to affect the upper layer and the lower layer. So this is what is happening in this moment. We are moving from IPv4 to IPv6. And IPv4 and IPv6 are in the network layer. So we are able to move from IPv4 to IPv6 without changing the upper layer and the lower layer, because we define well each layer, the functionality of each layer, and how each layer interact with the upper layer and the lower layer. Okay, if you have a model of reference like the OSI model, you have like a common language to compare different stack of protocol together. So the OSI model is important for that. Have a common reference model to compare a different stack of protocol, for example, the TCP/IP protocol stack or AppleTalk that was developed by Apple some time ago together, if you want to compare them. So AppleTalk is dead, no? Apple don't develop anything with AppleTalk anymore. And Novel Network also is dead, no? Now we all use TCP/IP. We might have other protocol that are around, but basically everything is TCP/IP. It is ubiquitous. It is everywhere in this moment. Okay, so I'm going to talk about the OSI model. So OSI stands for Open System Interconnection. And the international organization that developed the OSI model is called the ESO. And it stands for International Organization for Standardization. So the ISO defined the OSI model in 7 layers. So this layer, the lower layer, we call it layer 1. And it's the physical layer. Layer 2 is the data link layer. Layer 3 is the network layer. Layer 4 is the transport layer. 5, session layer. 6, presentation layer. And 7, application layer. So I'm going to talk about each of these layers. I'm going to use a top-down approach, which means that I'm going to start with layer 7 and go down to layer 1. So I'm going to say first what so the user, you, I, we are here. We are on top of layer 7. Sometimes they call the user layer 8. Of course, this layer 8 does not exist in the OSI model. So what is the application layer? It's a layer where we will define application protocol. So those protocols that will be used directly by the end user. So this is the layer that make connection of the OSI model with the end user. In this layer, we will find, for example, protocol to transfer file. So there are several protocols in the TCP/IP protocol suite to transfer file. Can you give me some example? So there is one that is called FTP. Have you heard about FTP? FTP stands for File Transfer Protocol. It's a protocol, it's an application layer protocol for the transfer of files. There is another one that is called TFTP, Trivial File Transfer Protocol. It's another protocol for the transfer of file. For example, there is another that is called Secure CP, which is part of Secure Shell. It's a more recent protocol. It uses encryption, it uses authentication, and it allows the transfer of file also. You will find other protocol for auto configuration of network devices. For example, one that is very famous is DHCP, Dynamic Host Configuration Protocol. So instead of configuring all your devices manually, which is very time consuming and error prone, you can use a DHCP server and configure all your computer, your end user computer, as DHCP client. When you put on a computer, it will communicate with the DHCP server and get its networking configuration. So there are several protocols here for auto configuration. It's not the only one. For example, we have BootP. Okay, protocol to do remote session, remote logging. We already saw in the lab that we did some of those protocols. So Telnet is one of them. The problem of Telnet, it was defining a long time ago, and it doesn't encrypt the communication. So we have a new web protocol that is called Secure Shell. And Secure Shell allow you to do remote session in a secure way. It means that it uses authentication and it uses encryption. There are other protocols, like, for example, remote shell, that allow you also to do remote session, no? We also have in this layer, which is the application layer, protocol to manage mail. So there are many protocols here. One of them is SMTP, Simple Mail Transfer Protocol. Another one is POP3, Post Office Protocol version 3. Another one is IMAP. So we have several networking protocols to manage email. So today you don't realize, because you use the front end that you use is always a browser. So you don't realize that there are protocols behind that. But we do have protocol to transfer mail, to exchange mail. Now, to do network administration, network management, we need protocol. For example, here we have a protocol that is called SNMP, Simple Network Management Protocol. It's a protocol that allows you to monitor your devices, your network devices, or to change their configuration. It's not the only protocol to do that. We have other protocols. For example, we have a protocol that is more recent, that's SNMP, that is called netconf, and we have also resconf. We have other protocols for that. So this is the application layer. Now, in layer 6, because I go down, we have the presentation layer. And in this layer, we will deal of a common representation. So, for example, if you want to represent characters in a communication, letters from A to Z, you need to convert those letters in numbers. Because at the end, in the computer, the only thing that we can store are numbers. So there are several tables that we can use to do that. There is one table that is called the ASCII table. So many computers today use the ASCII table. But at one point, IBM have a different table that was called the EBCDIC table. And today, we also have the Unicode. So if one computer use EBCDIC and another computer use ASCII, they will not be able to talk together. They need to agree to use the same way to represent the character. For example, both are going to say, okay, let's use ASCII. So the way that I represent a capital A is the same way that you are going to represent a capital A. This is what we want. We want a common presentation of the data. Okay, now integers. If we don't agree about standard, we are not able to exchange integer. For example, if I represent an integer over 4 bytes, and I communicate with a device that represents an integer over 2 bytes, we will have problem. So at the beginning of the communication, we do have to agree. Okay, we are going to represent the integer in 2 bytes, or we are going to represent them in 4 bytes. There is also something that is called little endian and big endian. So for example, Intel is little endian, but Motorola is big endian. What does it mean? The way that we position the byte when we represent integer. So little endian means that the byte, which is less significant, I will put it in the lower address. And big endian means that the byte that is less significant, I will put it in the upper address. So of course, if we are going to communicate a computer that uses Intel with a computer that uses Motorola, they do need to agree if they are going to use little endian or big endian. Otherwise, there is no possible communication. It's like, I speak Spanish and you speak English. Okay, if we don't agree of a common representation, there is no way that we can communicate. Also, in the presentation layer, we can negotiate, for example, if we want to compress the data or not. So of course, if we compress the data, we will need less bandwidth to transfer the data because we compress the data, we make it smaller. So of course, we need to agree. We have many compression algorithms. So the sender will compress the data, make it smaller in size, send the data. And the receiver will decompress the data and get the original data. Of course, that will be possible only if we are using the same compression algorithm. Also, in the presentation layer, we will decide if we encrypt or not the data. So we need a negotiation at the beginning because we have several encryption algorithms. For example, there is one that is called DES, another one that is called AES for Advanced Encryption Standard, another one that is called IDEA, IDEA for International Data Encryption Algorithm, another one that is called Blowfish. So if we decide to encrypt, and I encrypt using DES, and you, for example, use another encryption algorithm, we will not be able to do a communication because we need to use the same encryption algorithm, no? And for example, if we are going to transfer image, there are several formats to store the image. So also at the beginning, we need to agree. Okay, we are going to transfer the image in PNG format, or in GIF format, or in JPEG format. Okay, because if I represent all my image in JPEG, and the other computer represent all the image in GIF, and I assume that I can send a JPEG, the other computer may assume that what I sent is a GIF because it represents everything in GIF. So it's why in the communication at the beginning, we need to agree how we are going to represent an image. So those details of presentation are encapsulated in the presentation layer. When we go down in layer 5, we have the session layer. So in the session layer, it's where we are going to initiate session, maintain session, and close session. We are going to tear down session. So all the details related to session are there. For example, at the beginning of a session, we can negotiate if we are going to use simplex, half duplex, or full duplex. Do you know what is the difference between that? So let's say that we have two entities, A and B, and they negotiate a simplex communication between A and B. That will mean a communication where only A can send to B. B cannot send to A. It's called simplex because it's only a one-way communication. So half duplex, it's a two-way communication. So A can send to B, B also can send to A, but not at the same time. If A is sending to B, B cannot be sending to A at the same time. So we call it half duplex. And full duplex is when A can send to B and B can send to A at the same time. In this case, we call it full duplex. So at the beginning of the session, the two parties can negotiate if they are going to use simplex, half duplex, or full duplex. Another thing that is important is synchronization and recovery points. So if you go back some years ago, and people will download a big file from the internet, let's say that there is an ISO image of Debian, which is an operating system, and I want to download it. And it's a 4.3 gigabyte file. So in the past, you will start download it And if there is any problem with the internet and you have not finished to download the file, when the internet come back, when the communication come back, you have to start download the file from scratch, from the beginning. Because we were not maintaining recovery points. So today, when you transfer a file, you do maintain recovery point. Every specific amount of data that you transfer, you create a recovery point. So that if there is a problem of communication during some time, when the communication comes back, instead of starting the communication over and transferring the whole data, you just go and continue from the recovery point that you agree between the two entities that are transferring the file. So this is very important. This is part of the session, the recovery point and the synchronization. The transport layer. So in the transport layer, it's one of the layers where you will cut the data in smaller chunks before you transmit it. We already tell why it was important to cut the data in smaller chunks. Okay, to avoid starvation and to avoid retransmitting a long message if there is noise. So here also we can negotiate at the beginning if we want a connection-oriented communication or a connection-less or communication. So a communication-oriented communication is a communication where the protocol take care of everything. So for example, if there is a chunk of data that is lost, the protocol will take care of retransmitting this chunk of data. When you send, for example, two chunks of data through the internet, they can go through different paths. So you send the first chunk, then you send the second chunk. If they go through different paths, it's very possible that the second chunk arrived before the first chunk, because maybe it took a path that is faster. So the data can be not ordered at the destination. If your protocol is connection-oriented, it will reorder the data, because the data can arrive in disorder. Sometimes the network also recreate duplicates of a chunk. So if you have a connection-oriented protocol, it will take care of that also. If there are duplicates, it will remove the duplicate. So a connection-oriented protocol take care of all this. If chunks are missing, it will ask for retransmission of the missing chunk. If the chunks are in disorder, it will reorder them. If they are duplicated chunks, it will remove the duplicated. So we have exactly the data at the end as the sender sent it. Of course, a connection-oriented protocol, since it provides all these services, is much heavy than a connection-less protocol. So a connection-less protocol is very fast because it does not verify anything. It just sends the data. So if the data is lost, a connection-less protocol will not ask retransmission. If the data arrive in disorder, a connection-less protocol will not reorder them for you. If you receive duplicate chunk, it will not remove the duplicate chunk. So it's very fast. So some applications use connection-less protocol, and other applications use connection-oriented protocol. So here the same order delivery that is part of the connection-oriented protocol. Reliability, if you lose segment, you will retransmit them. If you have duplicated, you will just suppress the duplicate. Another thing of the transport layer is flow control. So I was telling you that flow control is a way for a computer to tell another one, or a network device to tell another one, don't send me more data for now. Let me process them. I'll let you know when I'm available again to receive more data. So multiplexing is also provided in this layer. So what does it mean? It means that, for example, in a server, you can have a web server, you can have a FTP server, you can have an email server. And this server will receive petition for different services. And it will be able to make the difference between, oh, this is a petition for the web server. This is a petition for the email server. This is a petition for the file server. So for that, in the transport layer, we use addresses. So each process will have an address. And this address in the TCP/IP protocol suite, we call it a port. So I'm sure you have heard about port. For example, if I tell you, what is the port that HTTP use? Do you know the port number? 80. What is the port that secure HTTP use? 443. You never heard about port before? Okay. So this is the way to create multiplexing through port. There are some terms that we define here. For example, in the transport layer, there is a term that is called end-to-end. So in this layer, we will talk about end-to-end. In this layer, we'll talk about host-to-host. And in this layer, we will talk about point-to-point. So when they talk about end-to-end, we are in the transport layer, which is layer 4. And what they mean by end-to-end is one process running in computer A is in communication with another process running in computer B. So we are talking about processes, specific processes running in a specific network device. When we will see host to host, we will see that we will talk about a communication between device A and device B, but we will not go at the level of the processes. And when we talk about point-to-point, we will talk about a networking card in communication with a networking card within the same link. So remember, we will have those terms, I'm sorry for that, end-to-end, host-to-host, and point-to-point. And end-to-end is in the transport layer. And here we have end-to-end communication. Let's go down. Let's go to the layer 3, which is the network layer. So the network layer is in charge of routing the packets. So the packet finds its way in the internet. For example, you are going to check a web page of MIT. So you send a packet from here, we are in JSU, to MIT. And the packet have to go through the internet. There are many routers. The way the packet finds its path is thanks to layer 3, which is in charge of routing the packet to the final destination. So in the network layer, we define addresses also, like in the transport layer. In the transport layer, the layer 4 addresses are called port. In the network layer, the layer 3 addresses are called hierarchical addresses, or logical addresses, or network addresses, or IP addresses. Here we will talk about communication host to host, which is from device A to device B. And here in the network layer, we also, if we need it, can cut the data in smaller chunks. When we can do it here in the transport layer, as we just saw, or we can do it in the network layer. When we do it in the transport layer, this is called segmentation. When we do it in the network layer, it is called fragmentation. So every time that you heard the term segmentation, you know that you are in layer 4. When you heard fragmentation, you know that you are in layer 3. But both of them is cutting the data in smaller chunks. And of course, reassembling is also task of those layers. If I cut in layer 3, I have to reassemble in layer 3. If I cut in layer 4, I have to reassemble in layer 4, which is called peer-to-peer. What layer 4 do in the sender is for layer 4 in the receiver. What layer 3 do in the sender is for layer 3 in the receiver. So here we talk about host-to-host communication, and we have routing protocol. So there are several routing protocols. One is called RIP, which is called Routing Information Protocol. There is another one that is called OSPF, Open Shortest Path First. ISIS, Intermediate System to Intermediate System. BGP, Border Gateway Protocol. EIGRP, Enhanced Interior Gateway Routing Protocol. So we have a lot of routing protocols, which are dynamic routing protocol, and we will talk about them in the future. Okay, let me go down. We were in layer 3. Now I go down to layer 2, where we have the data link layer. So in the data link layer, we define a method, the method to exchange information within a common media. So we are local. We are in the same link at the level of the data link layer. So the communication is called point-to-point. And as I was telling you, point-to-point is when you say from this network interface card to this network interface card that belong or that are connected to the same media. Okay, the data link layer is divided in 2 sublayers. So the upper sublayer is called the LLC sublayer, and the lower sublayer is called the MAC sublayer. So LLC stands for Logical Link Control Layer. And this layer allows me multiplexing. It's allow me to have, for example, in layer 3, different layer 3 protocol like IPv4, IPv6, IPX, that was done by Novell Network. It's also provide a way to control the flow. So if you remember, we talk about controlling the flow in the transport layer, and now we are talking about controlling the flow in the data link layer. When we control the flow in the data link layer, we control the flow in the same link. When we control the flow in the transport layer, we control the flow in 2 devices that are connected to remote network that are not shared normally. We define, for example, if there is an error in the transmission, the sublayer LLC is able sometimes to correct it. And this LLC sublayer is defined in an IEEE standard, which is called the 802.2. Now, the MAC sublayer, which is the lower sublayer here. We have 2 sublayers. The LLC is the upper, and the MAC is the lower. In the MAC sublayer, we define, for example, the method that will we use to access the media. So we have different methods. We have, for example, carrier sense multiple access with collision detection. We have token passing. We have polling. We will see those methods another day. So in those layers, we try to prevent collision. And of course, we try also to detect when there is a collision. Remember that the medium is shared, so only one device can transmit at a time. But it's very difficult to synchronize them and to say who is going to transmit. It's why we need a method to access the medium, and it is defined in this MAC sublayer. We can manage quality of service also, QoS. It's the place where we will manage VLAN, virtual local area networks. We define addresses also in layer 2, which are called MAC addresses, or physical addresses, or layer 2 addresses, or flat addresses. Here, a switch will take decision. A switch can do three things, as we will see. It can forward a frame, filter a frame, or flood a frame. This decision that take a frame, a switch story, that over a frame that it received is walk of the MAC sublayer. And you can do MAC filtering. So for example, in your access point, you can specify the MAC address of the devices that are allowed to use your internet connection. Remember, we have addresses in layer 2, the data link layer. They are called MAC addresses. We have addresses in layer 3, the network layer. They are called logical addresses or IP addresses. We have addresses in the transport layer. They are called ports. So we have addresses in 3 layers. And finally, the physical layer. So the physical layer will describe all the mechanical details, electrical details, functional and procedural, mean that we need to transmit bits across a physical connection. For example, in the physical layer, you will define the shape of the connectors. For example, we will use RJ45, or we'll use BNC connector. You will define also your media. For example, UTP cables, which are based in copper. We are going to twist the pair. All these details belong to the physical layer. Or for example, the way that you are going to encode and decode the series of bits. Encoding is transforming a series of bits into a signal. So this is part of the physical layer. If you are using fiber optic, you will change your series of 0 and 1 into pulse of light that will traverse the fiber optic cable and arrive to the destination, no? So those are details of the physical layer. The bit rate, if you are going to use 10 Mbps, Mbps means megabit per second. If you are going to use 100 Mbps, if you are to use 1 gigabit, which is 1000 Mbps, or 10 gigabit, which is 10,000 Mbps. So the bit rate is defined in the physical layer. If your communication will be serial or parallel. So serial is when I need to transmit a bit, I send 1 bit at a time. So first bit, second bit, third bit, up to the last bit, which is the 8th bit. Now, if you use a parallel communication, you have 8 wires. And in parallel, you send the 8 bits. So serial communication, with serial communication, we have longer distances. With parallel communication, which seem to be faster because we are going to send the bit in parallel, we have very short distances. So we seldom use parallel communication because it's just allow us very short distances, and we need long distances, no? Okay, the physical way, your topology, the way that you are going to connect the devices together. If you are going to use a bus or a ring or a star or an extended star, a mesh, a partial mesh, those topology belong to the physical layer. Okay, there is a term that we call the PDU, the protocol data unit. PDU is the way to say what is the name of the information in a specific layer. So the PDU in the upper 3 layer are called data, which means that the information are called data in the upper 3 layer, which is the session, presentation, and application layer. In the transport layer, the information that we want to send is called a segment or a datagram. In the network layer, the information that we want to send is called a packet. Then in the data link layer, it is called a frame. And in the physical layer, which is layer 1, it is called a series of bits. So when you listen frame, we are talking about layer 2 normally. When you listen packet, we are talking about layer 3. When you listen segment, we are in layer 4. So here, as I was telling you, the TCP/IP protocol suite starting as a project that was called ARPANET. And it interconnected at the beginning. When the Department of Defense released it, it interconnected 4 computers in the world. 4 computers that were in the US, 3 in California, 1 in Utah. Today, we are running out of IPv4 addresses, and we need to go to IPv6. So we have been in the migration for many years already, I think more than 20 years. And IPv4 is still the dominant protocol. Here we have the TCP/IP protocol suite, which is based on 4 layers, not 7 layers, like the OSI model. So in the lower layer, which is called network access layer, we have protocol like, for example, the address resolution protocol, the point-to-point protocol, and we have technology like Ethernet, Wi-Fi, WiMAX, Bluetooth, Zigbee, token ring. Okay, I'm sure you have heard about all this technology. In layer 3, we have, it is called in the TCP/IP protocol suite, it's called the internet layer. So we have protocol like IP, IPv4 and IPv6, ICMP. When you use the ping command, it uses this protocol, ICMP echo request, ICMP echo reply. And we have routing protocol like the Open Shortest Path protocol, the Enhanced Interior Gateway Routing Protocol, RIP, ISIS, and other protocol. In the transport layer, which is layer 4 of the OSI model, we have 2 kings. One is TCP, which is a connection-oriented protocol, and one is UDP, which is a connection-less protocol. So TCP is heavy because it's connection-oriented. UDP is light, very small protocol, runs very fast, but it's not connection-oriented, which means that UDP cannot correct. For example, if you receive the data in disorder, UDP will not correct it. If something is missing, UDP will not ask retransmission. Okay? If you have duplicated, UDP will not suppress the copies. It will keep the copies in the data that you will receive. On the application layer, we have protocol that we already mentioned. For example, for host configuration, we have DHCP. For managing email, we have simple mail transfer protocol, post office protocol. For the transfer of file, we have file transfer protocol, trivial file transfer protocol. To manage the web, we have HTTP or secure HTTP, no? Okay, I'm going to explain what is encapsulation. We already talked about that, and I was telling you that when you send a letter and you put it in an envelope, you are encapsulating. So encapsulation is something that appears when you send information. So when the information or the PDU go down the stack. When you send the PDU or the information that you are going to transmit go down the stack. And when you receive the information go up the stack of protocol. So encapsulation is the fact that when the data go down the stack, you will add, every time that it passes through a layer, you will add a header to this data, and you will send it down the stack. So encapsulating is adding information. And I add information for the same protocol in the computer that is going to receive the data, which is peer-to-peer. What TCP do in the sending machine is for TCP in the receive machine. What IP do in the sending machine, what IP will add is for IP in the receiving machine. So when the data go down the stack, all those protocols will add header. For example, let's take the case of the web. Here you have a web server, and here you have a web client. Let's say that the web server generates a web page for the web client. So it's going to send the web page to the web client, which is a browser like Chrome or Firefox, for example. So the web server has data. It will send the data down to layer 4, where we have TCP. TCP will cut the data if necessary. And TCP in each segment, in each piece of data, will add what we call a TCP header. In the TCP header, we will have port, which are addresses, which will identify here the web server, which is a process, and the web client, which can be Chrome, for example, which is also a process running in the web client. So in this header, we will have two addresses. The TCP source port will be what in this case? If we are sending from the web server to the web client, what will be the source port? It will be 80, because it will identify the web browser. And the destination port will be something that is associated with Chrome or Firefox that is running here in this client machine. Then TCP will send it down the stack, the PDU. At the level of TCP layer 4, it is called a segment. And TCP will send it down the stack to layer 3, where we have IP. IP will add a header. In this header, we will have an IP address for the source and an IP address for the destination. So the source IP address will be the IP address of this computer, the server. And the destination IP address will be the IP address of this computer, where we are a web browser that is running. Then TCP will pass the packet down the stack. In the data link layer, where we have Ethernet, Ethernet will add a header. In this header, we will have a source MAC address and a destination MAC address. So every time that the PDU go down the stack, each layer add a header. Adding a header is called encapsulation. Now, when the data travels the medium and is received by this computer, which is a client, we will have the inverse operation. The data is going to go up the stack, and every layer is going to remove one header. So for example, the data link layer will remove the header that the data link layer of the server added to the data. The network layer will remove the header that the network layer of the server added. It's why we talk about peer-to-peer, because what the network layer add is for the network layer of the receiver. And once the receiver process or use this information that was added in the header, it removes the header. So when the data go up the stack, we'll remove header. And this is called decapsulation. Okay, we have several international organizations that do standard. For example, here we have the Institute of Electronic and Electrical Engineer. Here we have the Internet Engineering Task Force. Those are very important. So I have a slide to go through them and to see what they do. So for example, the Internet Engineering Task Force define what we call the request for comment. So all the protocol of TCP/IP are defined by standard documents that are approved by this institute, the Internet Engineering Task Force, and they are RFC. So the IEEE, which is very important, is an international organization that defines standard in layer 1 and layer 2. For example, I have a slide here. The IEEE define the 802.3, which is Ethernet. So if you want to know how Ethernet works, you can read this standard. The IEEE also define Wi-Fi. So Wi-Fi is the name that people know. That people in your house that are not people in computer science, they call it Wi-Fi. But the name that we use normally is 802.11, because this is the standard of IEEE. Bluetooth, this is the name that people know, people that are not in the area of networking. This is this standard of IEEE, which is the 802.15.1. Zigbee is the 802.15.4. WiMAX is the 802.16 of the IEEE Institute, no? Another important is TIA, the Telecommunication Industry Association. They mainly define standards that are related to cabling. For example, the UTP cable that we use, they define those standards. So for example, what is a cable category 5? What is a cable category 5E, 6, 6E? They will define that. The International Telecommunication Union, telecommunication sector, define a lot of protocol that are related to IPTV. For example, codecs. When you encode the voice, you change the voice or sound. The sound is an analog signal, but we are going to put this signal as a digital signal. So when you do that, we have some standard to convert this analog signal to a digital signal. And this is mainly done by this ITU, International Telecommunication Union. TCP/IP was defined in 1970, 50 years ago. Can you imagine that? IPv4. We are still using IPv4. And we are moving to IPv6, not because IPv4 is not good. It's because we don't have enough IPv4 addresses. It was impossible for them to imagine that IPv4 will have that much success, because it was a project of the Department of Defense. It was not thought from the beginning to be spread all over the world. And you can imagine 50 years ago, it was very difficult to think that we will have several devices in our hand, in our body, that use internet, that need IP addresses, your cell phone and other devices that you carry. So it was very difficult for them to imagine that. So of course, the number of IP addresses that they imagine at this time is much lower than what we need today. So we are moving to IPv6 because of that. Here we have a comparison of the two protocols, the TCP/IP protocol suite in 4 layers and the OSI model in 7 layers. Okay, I'm going to talk about what is multiplexing and how it works. So I already say that. So let's say that we have a common medium. We share the medium. So if this person is transmitting, this person cannot be transmitting at the same time. If they do that at the same time, we will have a collision. So both of them want to access the server. So both of them send petition to the server, and the server send the answer back. So what they will do, the computer will do, is they will cut the information that they will send to the server in small chunk. And in the media, you will have chunk of this person and chunk of this person, and they will be alternate. There will not be only chunk of the green person or only chunk of the purple person. You will have chunk of the green and chunk of the purple person. This is called multiplexing, the fact that you are able to share a medium. Both of them have the impression that the medium is for them, because this is done so fast at the level of a human that we have the impression that the medium is our medium. So each piece must be labeled, must have a label that say who is the sender and who is the destination, no? One thing that they say here, the good thing of making a small chunk, I already told you, is that let's say that this chunk, when was sent, there were somebody that came and started the air conditioner. So the air conditioner have an engine, and this engine have a magnetic field. If you pass a UTP cable close to the air conditioner, it will put noise in the communication. You should not do that. But if you have done that, which it's a bad practice, I'm sure that when you put on the air conditioner, the beginning of the magnetic field will induce a lot of noise in your communication. So you will have some transmission that will be changed by the noise, and the destination will not be able to have the same information that the sender sends. So if you need to do retransmission, because you cut it in small chunk, you retransmit just a small piece, no? Okay, I'm going to skip this slide. I already explained what was encapsulation, what was decapsulation, so I'm going to skip these slides. Okay, so maybe I stop here for today. We just have a few slides to go, and then we are going to do exercises. So we have like maybe 4 or 5 slides to go. And look, I want to show you what I need you to go over. So in exercises, I think it's this one, the 4, exercises 4. We have a bunch of, yeah, it's this one. We have a bunch of exercises to understand all the terminology here. So if you look, we have 23 pages of exercises. So please start looking at them, and we will go over them. So by doing those exercises, you will understand all this concept that we saw today. I'm sure they are confused in this moment because it's a lot of terminology. You were not used to listen to this terminology, but since we are going to do those exercises, slowly by slowly, you will finish to understand them. What you need to remember is the layer of the OSI model and what is encapsulated in each layer. The layer of the TCP/IP protocol suite and which protocol we have in each layer. Okay, I will stop for today here. Thank you so much.